Let's look at the physics of a playground seesaw. We show the fulcrum with the triangular-shaped support. It's the point about which rotation takes place. A little girl sits at one end of the seesaw, and her boyfriend sits at the other end. Both the girl and the boy have equal weights. We label the forces involved, mg for each kid, and the normal N, the combined weight of the kids acting up at the fulcrum. The forces balance, and we see that the sum of the forces equals 0, the equilibrium rule in action. The kids are able to rock the seesaw up and down by leaning forward and backward in a way slightly shifting their weights. Kids do this all the time. But suppose one of the kids moves closer to the fulcrum. The system is no longer balanced. The girl soon rotates onto the ground, not shown here. For balance, a heavier kid needs to sit where the first boy sat. Then his weight multiplied by his closer distance to the fulcrum will equal her weight multiplied by her distance to the fulcrum. This brings us to a second requirement for mechanical equilibrium, that the sum of the torques on a system also equals 0, where Greek letter tau stands for torque. Equal and opposite torques can produce mechanical equilibrium. Let's drop in on one of my early City College of San Francisco conceptual physics classes and see this physics, not with a seesaw, but with a classroom meter stick.
Look at seesaws. Right now, I have my pivot point, the center of gravity. So what do we find? No rotation. It's not exactly centered in there. You get the idea, though. Put a weight over here. What happened? Wow. Put another weight over here. Now I'm talking about something you're all familiar with. Isn't that right? If these weights are the same, up and down, and this distance are the same, then we say the amount of torque that's tending to rotate it this way is just counteracted by what? An amount of torque rotating this way. And if those torques are the same, then I'll have no net torque, I'll have no rotation, if it's not rotating to begin with. And there we are. Isn't that neat? Now you know what's going to happen if I move this one in. I still have the same force acting over here, but I don't have the same torque. That's because my distance is less. And now it goes like that, okay? But I could have something like this. I could have playing with another partner. Suppose I could get something like this. You see, you don't have to have equal people, equal mass people playing on the same seesaw. Can you see that? Now, when it comes to balance, when it does, true or false, this weight multiplied by this distance will be exactly equal to this weight multiplied by this distance. Check the neighbor. Anyone say false? Okay?
Let's go back to our seesaw. As we've seen, kids can balance on a seesaw even if they have different weights. Whether they realize it or not, they position themselves so that the sum of the torques cancel to 0. Their torques will be equal and opposite. That is, the torque produced by the girl on the seesaw tends to rotate it counterclockwise, while the torque produced by the boy tends to rotate it clockwise. The two rotational tendencies cancel out. The torques are balanced. Here's something interesting. Even if the girl hangs below her end of the seesaw, balance remains. Why? Because although she's farther away from the fulcrum, her lever arm hasn't changed. The lever arm is the perpendicular distance from the fulcrum to the line of action of the force she exerts on the seesaw. We show the line of action with this purple dashed line. This imaginary line coincides with her weight vector and extends from far above the girl to the center of the earth. The distance between the left end of the seesaw and the fulcrum is the lever arm. always at 90 degrees to the line of action. Recall our treatment of a wrench in our previous screencast, where we defined the lever arm as the perpendicular distance between the line of action of a force and the pivot point. Getting back to our seesaw, we assume that the girl sits 3 meters from the fulcrum, the lever arm distance. Here she dangles 4 meters below the end of the seesaw. What's her physical distance from the fulcrum? That's right, 5 meters. Never mind the 5-meter distance. Her lever arm, as said, is 3 meters, just as it was before she decided to play around. Yum physics? I hope you think so. Let's conclude with an intriguing situation. Suppose our boy has no friends to play seesaw with. If he can reposition the fulcrum, would he be able to play by himself by leaning to and fro as with a partner? Wouldn't the seesaw itself be his partner? We showed the seesaw's center of gravity with the purple dot at its center. I want to leave you with a question. Suppose the boy succeeds by sitting on the far end after shifting the fulcrum beneath the seesaw's 1/4 mark, as shown. For rotational equilibrium, how will the boy's weight compare with the weight of the seesaw? Think about that. Until next time, good energy.